Hello there, students. This is Mr. Hatfield. Today I'm going to show you how to use the ionic and covalent simulation that I shared in class last week. I'm going to share my screen right now. So this simulation, again, is ionic and covalent bonding, and we want to try to use this simulation to help understand the difference between them. So we're going to use a periodic table, we're going to use Lewis dot structures, and we're going to use some logic. Now the first thing is, we'll notice that we have this periodic table and we have some elements that are highlighted. And what is not obvious is that we have some things that are to the left and some things that are to the right of the stair-step line. So if the stair-step line was here, we would see it right around boron, in a little diagonal, silicon, arsenic, and all that. We would see it around that area. So everything over to the left of that imaginary line is a metal. And so we have sodium, magnesium, aluminum, potassium, and calcium, all metals. But on the opposite side of the stair-step line, we have nonmetals: nitrogen, oxygen, fluorine, sulfur, and chlorine. Now you may say, well, that's very good. I mean, but why do we care here about the imaginary stair-step line? Well, we want to understand that some are metals and some are nonmetals. Because the big idea is that when we're talking about ionic bonding, we're talking about a metal combined with a nonmetal. Whereas when we're talking about covalent bonding, we're talking about two nonmetals together. So let's do an ionic bond first. And we're going to do sodium and we're going to do nitrogen. Now, the moment after we do these, let's compare the data that we have for each one. Sodium symbol is capital N, little a. It is a metal. It has a low number for electronegativity, less than 1, 0.93. Nitrogen, on the other hand, symbol capital N, is a nonmetal, and its electronegativity is high, 3.04. Now, what that means is that sodium can't really grab its electron very strongly, and nitrogen only grabs its electron with much greater strength, but nitrogen is greedy. It will try to grab even more electrons if you give it a chance. Now, how many will each want to grab? Well, sodium is not very good at grabbing. In any case, the Lewis dot structure for sodium shows that we only have one valence electron. We only have one electron on the outside, which means we have a bunch of empty spaces. In fact, 7. Whereas with nitrogen, we have 5 dots, 5 valence electrons. And so there's only a few empty spaces. 1, 2, 3. 1, 2, 3. But again, nitrogen is so electronegative, so greedy, it will try to grab an electron from anything it can to fill up those spaces. And it's going to pull on electrons a lot more. Now, sodium, of course, can't pull back. It can't resist nitrogen because nitrogen's electronegativity is more than 3 times greater. So sodium can only give up an electron. But notice also that sodium can only give up 1 electron. Again, nitrogen has 1, 2, 3 empty spaces on its outer shell. It's going to want to try to fill all of them. This kind of arrangement, when one element is giving up an electron, the other element is stealing the electrons aren't being shared. One is being lost and the other is just taking it in a greedy fashion. And so this is an ionic bond, because an ionic bond, the electrons aren't shared. Instead, they are stolen. Now, we know we have at least 1 nitrogen and we have 1 sodium. But if we submit that answer, it says it's not correct. And then we think again and we realize, oh yes, sodium doesn't pull very hard. Nitrogen is going to be the one that does the pulling because it's more electronegative, and it wants 3. Nitrogen wants 3 electrons. So 1 sodium only has 1 electron on its outer shell. 1 sodium is not going to be enough. So we're going to need to have 3 sodiums for the 1 nitrogen. Now, the moment we admit that, and we now see this animation occurring over and over again, very helpful. So we start off with a sodium. There's actually 3 of them, and each of the 3 sodiums has 1 dot, which means that they have 1 valence electron. We're going to have 1 nitrogen. It's got 5 dots, which means it has 5 valence electrons. And again, the nitrogen, because it's far more electronegative, it will pull on the electrons of the three sodiums much more than they can resist. And so each sodium is going to be stripped of its valence electron. Now look what happens afterwards. Both the elements end up in brackets. We have 3 brackets for the 3 sodiums, and we have 1 bracket for the nitrogen. Now the sodium in the brackets, all 3 of them, there's no dot. They've clearly lost. Their valence electron. And whereas you can see for nitrogen, it goes from 5 to 8. It's added those 3 electrons to fill out its outer shell, to complete its octet. Finally, outside the brackets, we see plus signs immediately outside the sodiums and a -3 outside the nitrogen. Why? Because the sodium ion has a charge of +1 because it lost its electron. And it has now 1 more proton in its nucleus, 11, than electrons on its outer shell, 10. Whereas nitrogen has gained 3 extra negatively charged electrons, and so it is -3. And of course, at the bottom, we see the formula for this compound, Na3N, and the name is sodium nitride. Now, if we go to the document that goes along with our simulation, we see the URL, the web address, and we see an image that matches the simulation we see on the screen. We see this declaration that says ionic bonding takes place between a metal and a non-metal. And then underneath that, we have a table. And so this table actually has the first example already done. We put a sodium together, we put a nitrogen together, and the formula is Na3N. And then we have the Lewis dot compound, and just the way we see it, and then the name. Now, how can we go about actually putting something like that in our document? Well, we type Na3N right here, and you would select the 3 and go up here until you saw the subscript button, X of 2 on the bottom, and that would put that there. What about how do we make the symbol for sodium in a bracket? Well, we'll press a bracket. We'll write the symbol inside, and then on the outside, we'll put a plus sign. What about the nitrogen, though, that has the dots inside it? Well, that one's a little bit harder to do, but it can also be done. We can go 2 periods, ... and then bracket, colon, capital N, colon, reverse bracket. We'll put -3 on the outside here, and now we'll just put 2 periods underneath, and we can line them up nicely like that. And as a final touch, go to -3 and make that a superscript. So you can do those things. You can enter them. It's a little time consuming. Now, if you say to yourself, well, that's a lot of trouble and work, I'm not sure I have the time, but I get what to do here. Well, if you don't want to fill out the document this way and make it nice and neat, you can do it by hand. But keep in mind, if you do it by hand, you have to create the entire table by hand, and you have to draw in things rather than creating them through Word. Either way will work. But that's what you'll do, right? You're just going to go through, and whatever you're given, that's how you'll do that. And there's a series of problems for sodium in one table, a series of problems with magnesium in a second table, and 3 problems for aluminum in a third table. Now let's talk about covalent bonding, which takes place between 2 nonmetals. Head back to our simulation now. We're going to do 2 nonmetals, and the ones we're going to do nitrogen, nonmetal, and fluorine. And we're going to do covalent bonding. Now, in the previous example, we cared about charge. We cared about which thing would become positive and which thing would become negative. Well, the metal always becomes a positively charged cation, either +1, +2, or +3. And the nonmetal always becomes a negatively charged anion, either -1, -2, or -3. So that's kind of a nice little, neat little regular pattern. That's what happens with ionic bonding. And I suppose the Lewis dot structures help us a little bit in figuring out what to do there. But here now we're going to have two nonmetals. In fact, they're both nonmetals that on their own would tend to become negative. But we're not going to investigate the charge at all because it doesn't matter. Because here, what's happening is we're not going to be held together by a difference in charge. Here, we're going to be held together because we're sharing electrons. Remember, with the ionic bond, we're not sharing electrons, we're stealing them. And one thing loses one and becomes positive, the other gains one or more and becomes something negative. So what's going to happen here instead is that we are going to share electrons. That means they're actually going to be going around more than one atom at the same time, which is remarkable. So again, for nitrogen, the Lewis dot structure is 5 dots, which means we have 3 empty spaces. Nitrogen needs 3 dance partners. And we have fluorine, which has 7 dots, 7 valence electrons, and only 1 empty space. And in order for nitrogen to be complete, it has to find 3 partners. And since the fluorine only has 1 empty space, 1 place to share, 1 fluorine is not going to do it. We're going to need 3 fluorines. But first, let's select that it's a covalent bond. And then we'll have 1 nitrogen and 3 fluorines. And we'll submit our answer. Once again, as before, we're going to see the same animation repeated over and over again. So notice what happens. 1 nitrogen will approach 3 fluorines, and the 5 valence electrons, and each of the fluorines has 7. Now, if you have 5 valence electrons and you're in group 5A, that means you have 3 empty spaces, like nitrogen. And if you have 7 valence electrons, you're in group 7A, and that means you only have 1 empty space. So what's going to happen is that the electrons aren't going to be stolen. Instead, they're going to be shared. And so nitrogen will share 1 electron with each of the 3 fluorines. And then when they come together, we write them like this. And the way we write them is that such that the nitrogen is clearly connected to the 3 fluorines, and all of the atoms, the 1 nitrogen and the 3 fluorines, are all surrounded by 8 dots. 8 valence electrons. That is, they have full shells. They all follow that octet rule. And of course, the formula is NF3, nitrogen trifluoride. And then we give you an additional piece of information. The fluorines tend to pull the nitrogens all in opposite directions, and so you get a shape that's said to be trigonal pyramidal geometry. That just means it tends to have a shape kind of like a pyramid. So good information to have. Okay, we go back to our document. And now we're looking at this for covalent bonding, and we see our formula. There's a place for the formula in F3. There's a place to write out the Lewis dot structure the way you saw it. It's nitrogen trifluoride is the name, and the geometry is trigonal pyramidal. Okay, so again, you can enter this by hand, occasionally using buttons to change the script. You can create the Lewis dot structure very easily by hand using a few periods and a few other symbols. So colon, F, colon, N, colon, F, colon, and then underneath, dot, dot, space, dot, dot, space, dot, dot. And that's a pretty good approximation, didn't take long. And the name is nitrogen trifluoride. And the geometry is trigonal. That means it has, 3 angles or pyramidal. Now, again, if you prefer, if you find it too taxing to figure out how to use the symbols that are available to you to represent a Lewis dot structure inside the Word document, you can simply create a table and you can draw the structure out yourself. And that has the added benefit that you can make it as big as you need it to be in order to make the drawings comfortable. Just remember, if you do it that way with the drawing, that's fine, but instead of sending a Word document attached, you would send picture or pictures of your work attached. Probably going to need pictures because you have multiple tables. You won't be able to get them all on the same piece of paper. All right, so there you are, students. That was a brief demonstration. It's not hard to use. You can see as you work your way through it, you'll be able to clearly compare ionic bonding, which involves charges being moved around, electrons being stolen, being swiped, and compare that with the much more powerful covalent bond in which electrons are shared. The Lewis dot structures can help you understand both, but they're especially helpful when we consider the case of the covalent bond. I hope that was helpful, and I look forward to seeing you in class again soon. Bye-bye.